This video is all about differentiating exponentials and logarithms. Exponentials we dealt with in year 12. We saw that when we're differentiating e to the power x, we get e to the power x, as in nothing changes at all. The power stays the same, the base stays the same. And that was what was so special about Euler's number e. Remember, e is approximately 2.718. And that's what's special about this number 2.718, the fact that it is its own gradient function. That only works with e to the power x. If I had 2 to the power x, or if I had 3 to the power x, or 4 to the power x, or so on and so on and so on, it would not differentiate to be itself. It would differentiate to be something else entirely. And we'll do that later on in this unit of work. But for now, the exponential differentiates to be the exponential. The power doesn't change, the base doesn't change. Exactly the same thing. We also saw in year 12 that if there is a constant number on the inside of the function, then the only difference is we're going to multiply by that number. Again, the power stays the same, the base stays the same. The only difference is we're going to multiply by that k. So this all stays the same. We are just going to multiply by the k. That's an example of something called the chain rule that, we're going to be doing in a lot of detail later on in this unit. So that's about differentiating the exponential. Differentiating the logarithm, we didn't see that in year 12. This is going to be brand new. When we differentiate ln x, we get 1 over x. And I'm going to prove that result to you shortly. So, first let's have a look at an example of differentiating exponentials. So here this question's asking me to find the equation of the tangent to the curve y equals e to the power 2x minus 3x when x is 1. And I need to give my answer in exact form. So tangent, I'm thinking y equals mx plus c because it's a straight line. And I'm going to need to differentiate my curve to get the gradient function. So, when I'm differentiating e to the power 2x, I will have 2e to the power 2x. The power stays the same, the base stays the same. I just need to multiply by the 2. Then we've got this minus 3x there. So if I differentiate that, I get minus 3. So this is my gradient function, 2e to the power 2x minus 3. And I want to work out what the gradient is when x is 1. So let's substitute 1 into that. So we'll get 2 times e to the power of 2 times 1 minus 3, which is 2e squared minus 3. Now, don't touch your calculator, because we need to leave our answer in exact form. So I'm going to leave the gradient in this form here. That's the gradient of the tangent in exact form. So y equals mx plus c, y equals m. I'm going to put that in brackets because that's the whole m, x plus c. To work out my c, I need to substitute a coordinate in. I know that the x-coordinate is 1, but I don't know what the y-coordinate is yet. But I can work out the y-coordinate by substituting 1 into the original function. So let's do that. That will give me y equals e to the power of 2 times 1 minus 3 times 1, which is e squared minus 3. And again, don't touch your calculator. We want it in exact form. So that's the y-coordinate in exact form. I'm now going to substitute those into my y equals mx plus c. So we're going to substitute the y coordinate in here, and we're going to substitute the x coordinate in here so we can work out what that c is. So 2e squared minus 3 times 1 is just going to be 2e squared minus 3. I'm now going to add 3 to both sides, which will cancel those out. And then if I subtract 2e squared from both sides, e squared minus 2e squared is minus e squared. And so that is my c value. And therefore, the equation of my tangent is y equals the m, the 2e squared minus 3x, plus the c, which is minus e squared. And that's the equation of the tangent in its exact form, where x is equal to 1. Just to show you what that looks like graphically. Here in red, you can see we've got the curve e to the power 2x minus 3x. And in blue, we've got the equation of the tangent, which I just worked out. And then you can see we've got the point 1 e squared minus 3 marked on to my graph here. And you can see that, yes, the blue line is a tangent to the curve of the red line at that point. Right, so that's exponentials. What about logarithms? So I showed you a moment ago that ln x differentiates to be 1 over x. You might need to prove that. So this is how we're going to do that. Because I don't know how to differentiate the logarithm, I'm going to remove it by taking exponentials of both sides. So I will have e to the power y is equal to x. So now I've removed the logarithm, I can now differentiate both sides. I can differentiate both sides with respect to y, because I know that e to the power y is going to differentiate to be e to the power y. It doesn't change at all. So if I differentiate this side with respect to y, and I'm going to differentiate this side with respect to y, then like I say, on the left-hand side, e to the power y differentiates to be e to the power y, and on the right-hand side, I'm going to have dx by dy. And I'm going to do something a little bit naughty here. When it comes to university level maths, you'll learn a bit more about this. But for now, I can get away with doing something a little bit naughty. I'm going to do the reciprocal to both sides. So I'm going to do the reciprocal of e to the power y, which is 1 over e to the power y. And on the right-hand side, I'm going to do the reciprocal to get dy by dx. So I've got my gradient function, dy by dx. And now I'm just thinking, well, I'd like it to be in terms of x, not in terms of y. So what is e to the power y? Well, if you remember back shortly, a few moments ago, e to the power y was equal to x. So I can replace that e to the power y with x. And there we have it. I've proved that when we differentiate ln x, we get 1 over x. Let's now see an example of me using that. I've already shown all my working out here, but I'll just talk you through it. In this question, we've been given the curve, which is 3 ln x plus 1 over x, where x is greater than 0. And we've been told that P is a stationary point. We need to work out the x-coordinate of P. So stationary point, I'm thinking that the gradient f dash needs to equal 0. So I'm going to differentiate this thing. Now, I've just proved a moment ago that if I've got ln x, that differentiates to be 1 over x. Here I've got 3 of them. So I've got 3 lots of 1 over x. So times that by 3, and I get 3 over x. So 3 ln x differentiates to be 3 over x. Then I've got this 1 over x here. To differentiate that, all I did is I rewrote that as x to the power minus 1, which then allows me to times by minus 1 and take 1 away from the power. And you can see that I then just rewrote that as minus 1 over x squared. So the 3 ln x differentiates to be 3 over x, and the 1 over x differentiates to be minus 1 over x squared. And that needs to equal 0 at a stationary point. Then I have decided to multiply through by x squared to get rid of those fractions, to get rid of the denominators. So I've times by x squared here, I've times by x squared here, and I've times by x squared here. So this 3x squared over x, the x's cancel out and just give me 3x. Here I just get 1. 0 times x squared is 0. And so I find that the x coordinate of the stationary point is that x is 1/3. For the second part of this question, I was told that point Q on the curve has got x coordinate 1, and I needed to work out the equation of the normal to the curve at that point. So normal, I'm thinking y equals mx plus c, but I'm also thinking negative reciprocal. In order to work out what the gradient's going to be, I'm going to use the gradient function. So I'm going to use this 3 over x minus 1 over x squared. If I substitute 1 into that, so I get 3 over 1 minus 1 over 1 squared. So that's 3 minus 1, which is 2. So the gradient of the curve is 2. Which means that the gradient of the normal is going to be the negative reciprocal, because the normal is perpendicular to the curve. So I get minus 1/2. In order to work out my plus c, I want to know a coordinate that I can substitute in. I know that the x coordinate is 1. So if I substitute 1 into the original function here, that's going to tell me the y coordinate. So that's exactly what I've done. I've substituted 1 here, and I've substituted 1 here, and that gave me the y coordinate of 1. I have then substituted that coordinate into my curve here, so I've substituted a 1 here, I substituted a 1 here. Minus 1/2 times 1 is minus 1/2. That's then allowed me to work out the c as being 3 over 2. And that's given me the full equation of the normal there. So there we go. That's how we differentiate exponentials and logarithms. Those are the 3 results you need to know and be able to use.